Hi, I'm Nikita. I'm here to represent Strathclyde University. Together, we're going to have a presentation about marine engines modeling. First, we're going to talk about the importance of marine engines modeling. I'm going to show you some tools that you can use. And then we're going to see a program that was created by Dr. Theodokatos from Strathclyde University, and we're going to do some case studies together. Okay. First, we're going to talk about the importance of marine engines modeling. It's for the better understanding of the physical processes, to investigate the interaction between the various subsystems, for the testing of alternative design options, and to examine circumstances with high risk in installation. The question is why we don't build the actual model and test it. And this is because of the very high cost and the huge amount of time needed. We're going to continue with some simulation tools. They're very simulation different components. The function of real engine processes is enhanced as the complexity of the simulation tool is increased. But more input data are needed. The execution and the model usage becomes boring. The transfer function models, they're the simplest ones and do not include in-cylinder thermodynamic calculations and are mostly used to develop engine control schemes. The next category are the mean value models. They're used for fast transient power plant performance estimation and are used as well for the engine control system design process. Their accuracy is around 5%. Then we have zero or one-dimensional models. They use a more detailed modeling of the dynamic processes inside the engine components. They are used for the performance prediction and transient response status. Their accuracy is 2%. We have the three-dimensional models like FEM or CFD, which are used for the development, investigation, or optimization of power plant components design, where the evolved processes take place in three dimensions. Some examples are the engine combustion chamber design, the propeller design. In this slide, we're interested to think about the different tools. We're going to continue with the mean value models. As I said before, there are a compromise between the simpler function models and the elaborate or four-dimensional models, and therefore they have been widely used to examine the engine and develop control schemes. Their advantages are that they have an acceptable accuracy, they need a limited amount of input data, and they have a reasonable time for execution. The drawback is that they require data for the calibration of the model. For the mean value models, we have two categories. The first one are the quasi-steady models, where no mass accumulation is considered between the engine components. And then the second category, where the modeling of engine receivers is as open systems. Here is the engine components modeled, and so the typical propulsion plant is a merchant vessel. As we can see, it consists of the engine, the shafting system, and the propeller. There is also a turbocharger unit, so that the power produced by the engine is maximized. The turbocharger consists of a compressor and a turbine on a common shaft. The engine exhaust gas is expanded in the turbine, thus producing work, which in turn is utilized to the compressor for compressing the air. In consequence, the pressure and as a result, the density of the air contained in the engine intake manifold is increased. Thus, the amount of air entering the engine cylinder is greater, allowing more fuel to be burned, and as a consequence, the engine produces more power without increasing the engine size. We also have the engine air cooler, which is located after the compression in order to cool the hot air exiting the compressor. Also, there is a scavenging receiver, the exhaust gas receiver, and the engine cylinders. We can see that the engine crankshaft speed is represented with the NE and the turbocharger shaft speed with the NCC. Now, for the calculation of measurements, we use the angular momentum conservation equations, where with the Q we represent the torque of the engine, of the propeller, of the turbine, and of the compressor. With the I, we represent the polar moments of inertia of the engine, the shafting system, the propeller, and the turbocharger shaft. And with the small n, we represent the efficiency of the shafting system. Now, for the calculation of the engine scavenger and exhaust receivers, we, as I said before, their model is open thermodynamic systems. The working medium mass at the M, the temperature T, and the pressure P are calculated using the mass and energy balances and the ideal gas loss equation. So the model includes 6 nonlinear first-order differential equations. The mass and energy conservation equations for the engine scavenging and for the exhaust gas receiver, and the 2 angular momentum equations for the shaft. In this slide, we have the model that was created by Dr. Theodokatos. It used the cycle mean value modeling. The objective of this work is to present a comprehensive but easily handled tool for the simulation of the overall ship propulsion plant, so that the initial tests of various design options, the interactions between the various components and control scenarios for the main engine, as well as the propeller pitch control, can be investigated. In that respect, the mathematical modeling of the overall ship propulsion system is implemented in the computational environment MATLAB Simulink. As we can see, there is a modular modeling structure. The engine components are modeled by using individual blocks capable of representing the involved processes. We have connection between the adjacent blocks, which are used for exchanging the required parameters. So, flow controllers, which is the compressor, the turbine, and the engine cylinders. We have the flow receivers, the engine receivers, elements like the engine crankshaft and the turbocharger shaft. We have fixed fluid, a propeller, which is connected with the engine crankshaft without a gearbox on a two-stroke engine and with a gearbox in a four-stroke engine. We have the engine governor, which is used to maintain the engine speed at the desired value by controlling fuel injection. And here we use a PID controller to model the governor. And also we have the orange block, which is the order speed schedule. We're going to continue with some case studies. Studies will be in steady-state operating conditions, where the engine is considered to operate under frozen speed and fixed load with constant fueling. And we will have some case studies in transient operating conditions, where it is investigated the dynamic response of the plant under severe transients, such as rapid load changes. This can happen from weather conditions, crash stop maneuver, and changes in the requested engine speed set point. Is a two-stroke marine diesel engine from MAN diesel and turbo, which was simulated using the mean value model. The engine steady-state operation was examined, covering the operating region from 50 to 100% load. A set of the predicted engine performance parameters, including the receiver's pressure and temperatures, the temperature of the exhaust gas exiting the engine, the turbocharger speed, the brake-specific fuel consumption, the brake power, and the total air-to-fuel ratio is presented in this figure. The respective parameters value obtained from the engine shop trials and from engine manufacturer web application for various engine loads are compared to the results of the simulation. It is obvious that the module provides adequate accuracy for modeling the engine performance in the whole engine operating envelope. In the next slide, it's the same case study, the same two-stroke marine engine, but after the previous validation of the model, here the engine is tested at slow steaming operation. So instead of the blowers activation, which are used on low loads for the charger supply, as an alternative, we model the cutout of one turbocharger unit. With the cutout of one turbocharger for slow steaming, the operator has the option to disable one of the engine turbochargers. So here we have the comparison of engine parameters in these two cases for engine loads below 50%. In this case study, we have a two-stroke marine diesel engine from MAN Diesel and Turbo, which was simulated using both approaches of the mean value model. Here we have the comparison of the approaches of the mean value model for fast engine transient run of 100 seconds with speed changes. As observed from the figure, the engine parameter responses, including the exhaust receiver temperature, are predicted with very satisfactory accuracy using the second mean value approach. The second value, as I said before, is the engine receivers are modeled as open thermodynamic systems. This is attributed to the model detailed modeling of engine receivers. Adequate agreement in the prediction of engine parameters, except for the exhaust receiver temperature, is also obtained using the first approach. In the first approach is when no mass accumulation is considered between the engine components. In the next case study, we have again a two-stroke marine diesel engine, which was simulated using, again, both approaches of the mean model. The comparison of approaches is on slower engine transient runs of 1200 seconds with speed changes. It is obvious that cases of slow transient, which are usual for ship propulsion plant operations, the engine operating parameters are also predicted with sufficient accuracy using the first approach. Some zero simulation. The difference between cyclic mean value models and zero one-dimensional is that mean value models are based on the assumption that engine processes can be approximated as a continuous flow through the engine, and hence average engine performance over the whole operating cycle. As a consequence, the in-cycle variation degree of internal parameters such as pressure and temperature cannot be estimated. On the other hand, two-dimensional and one-dimensional models operate per crack angle basis. So, in the zero simulation, the engine model is a control volume type model that calculates the cylinder processes in a degree-to-degree crank angle resolution. The control volume models treat a model as a series of thermodynamic control volumes interconnected through valves or ports. Work, heat, and mass transfer take place across the boundaries of the control volumes. This is achieved by applying the conservation equations in appropriate form to each control volume. So, engines have several flow receiver elements, control volumes, interconnected by flow controller elements. The flow receiver elements considered in the present study are the cylinders, the scavenging receiver, and the exhaust receiver. while the scavenging ports, the exhaust valves, the compressors, and the turbines were the flow control elements considered. The engine environment is regarded as a fixed fluid element, constant pressure, temperature, and composition. In order to simulate the overall system, the concept of the mechanical element is used, like the crankshaft element, the shaft element, and the shaft load element. It is used to model the propeller. In this slide is shown the part of cylinder block representing the cylinder number 1, including the scavenging ports and the exhaust valve. The engine cylinder is subdivided into 3 zones: a zone of pure air, a zone of combustion products, and a zone comprising air and exhaust gas. Within each zone, the temperature is assumed to be uniform but different from each zone. The pressure throughout the cylinder is uniform at any instant. For the calculation of the cylinder working fluid, thermodynamic parameters, the mass and energy conservation laws, as well as the ideal gas state equation in the controlled volume that encloses the cylinder, are used. Case study, we're going to use a large two-stroke diesel engine. In this slide, we can see the engine parameters, the bore, the stroke, the number of cylinders. Here we have a simulation model configuration. We have 9 cylinders with the exhaust valve and inlet ports, 3 turbochargers with the air coolers and the exhaust gas, and scavenger receivers. Here we see that the results derived from simulation runs for transient operation of the engine were validated against measurements, and the satisfactory agreement was observed. With the continuous line, we have the measured parameters, and with the dashed one, we have the predicted one. In this slide, we have the steady state of simulation results and comparison with the soft trial data of the operation of a two-stroke marine diesel engine. Adequate agreement in the prediction of engine parameters and the measurements is shown. The predictions are with the black line and the measurements are the red ones. Now, for the same case study, we have the engine, the in-cylinder pressure and temperature variations per crack angle and various loads. Here we have some three-dimensional models using CFD. They're used for design studies because they can help with geometry assembly, mesh generation, and analysis. Here again, we have a three-dimensional simulation. It uses CFD for the combustion simulation. We can see all the phases of the combustion. We can even see the particles of the injection of the fuel. And in this case study, we have measured the nitrogen oxide emissions. We can see that the measured ones with the black line have adequate accuracy with the prediction of the simulation, which are the ones with the red line. We're going to continue with a case study on a dual fuel engine. LNG is a very efficient way to cut emissions. All sulfur oxide emissions are almost eliminated because gas fuel doesn't contain sulfur. And the nitrogen oxide emissions are reduced by about 85% due to the high air-to-fuel ratio. This clean burn concept means that the quantity of air in the mixture of gas and air fed to the engine's combustion chamber is more than is required for all the fuel to be fully burned. Lean combustion technology reduces the temperature of the combustion process, and this reduces the amount of nitrogen oxide. Also, since there is excess oxygen available, the combustion process is more efficient and more power is produced for the same amount of fuel. We can also say that the carbon oxide emissions are reduced by about 25 to 30% thanks to low carbon to hydrogen ratio fuel, and emissions of particulate matter are almost eliminated. In this case study, we will have a dual-fuel marine engine. It can run in diesel mode, where the combustion of the diesel and air mixture takes place in diesel cycle, or it can run in gas mode, where the 99% of the fuel is gas and the 1% is diesel, the pilot fuel. It is a premixed combustion. The combustion of the gas and air mixture takes place in an Otto cycle, with ignition being triggered by the injection of the pilot fuel. The gas is mixed with air before the intake valves during the air intake period. After the compression phase, the gas-air mixture is ignited by a small amount of liquid pilot fuel. The air-gaseous fuel mixture does not auto-ignite due to its high auto-ignite temperature limit. The pilot fuel is injected near the end of the compression stroke to ignite the gaseous mixture. Diesel fuel auto-ignites and creates ignition sources for the surrounding air-gaseous fuel mixture. The pilot liquid fuel injected by the conventional diesel injection system contributes only with a small fraction in the engine power output. After the working phase, the exhaust gas valves open and the cylinder is emptied of exhaust gases. Here we have the engine characteristics. The investigated marine dual-fuel engine steady operation at both diesel and dual-fuel modes was examined by performing simulations in a low rate from 25 to 100 degrees percentage and constant engine speed at 514 RPM. A set of the derived results, including on the left we have the cylinder maximum peak pressure. On the right, we have the maximum in-cylinder temperature of burn zone, and then we have the indicated and brake mean effective pressure and the air-to-fuel equivalence ratio. Also, we have the brake-specific energy consumption, brake efficiency, and specific nitrous oxide emissions and carbon oxide emissions. With the blue line, we have the diesel mode, and with the green line, we have the dual-fuel mode. In the present study, a marine four-stroke dual-fuel engine was investigated by using GP Power software, which uses one-dimensional modeling. The main findings of the conducted research are that the engine in the dual-fuel mode operates with almost constant air-to-fuel equivalence ratio, around 2.2, whereas much higher values of the air-fuel equivalence ratio are used for the diesel mode corresponding to greater airflow. In the dual-fuel mode, the engine operates at lower receivers and in-cylinder pressure level. However, the mean effective pressure and power output is kept at the diesel mode levels. The dual-fuel mode is more efficient than diesel mode for loads above 70%. However, less efficient operation was observed at the lower load region. The carbon oxide emissions in the dual-fuel mode reduced 25% in average due to the natural gas low carbon to hydrogen. Larger reduction is taken at the high load region, where the efficiency than that in diesel mode. Also, the nitrous oxide emissions were reduced by 85% in average in the dual-fuel mode compared with the diesel mode. The diesel mode complies with the Tier 2 limits, whereas Tier 2 limits are met in the dual-fuel operation. In conclusion, it can be stated that the utilization of natural gas, which can be stored and handled in liquefied phase, provide an attractive and environmentally friendly alternative that should be considered and adopted in the future ship designs.